Okay, so we'll today know what are equipotential surface. So as you all already know, I told you that surfaces which have same potential, right, at every point are called equipotential surfaces. Alright, so let us first write the properties. What are the properties of equipotential surface? So the first one is that no work is done in moving a charge from one point to the other.
Okay.
One point over equipotential surface. So let us prove this with an example. Let us take an equipotential surface.
Yeah.
The potential at any point on this surface is equal. So let us take 2 points A and B on this surface. And
which page are we on?
we are on 2.15.
Okay.
So these 2 points will be having the same potential already because they are on equipotential surface.
Yeah.
So let us draw a vector from A to B, alright? And let this length be dl. Okay, so if we want to move a test charge which is placed at this point, at A we have a test charge Q0, we want to take it up to B, alright?
Yeah.
Then what would be the work done? WAB, alright? So we did that relation earlier, V is W by Q, right? So what will be W then? Potential into charge that is being taken from one point to the other. Q0 is that charge multiplied by the potential difference between the 2 points, right? What is that? Final minus initial, WB minus WA. This is the amount of work done. Now, as we know that we have assumed it already that this is equipotential. Okay. So on equipotential surface, what should happen is that the potential at A should equal the potential at B. Alright? For equipotential surface. Then WAB be how much? This would amount to 0 because they are equal. Q0 into 0 would be 0. Alright? That proves that no work is done in moving a charge from one point to another. Because the potential at every point is same, the work done would be 0. Alright?
Yeah.
Got it. This is the first property of equipotential surface, that you can move any charge from one point to other without doing any work. Okay. Second property is the electric field is always normal to the equipotential surface. The electric field EF is always Normal means perpendicular, okay, to
Okay.
equipotential surface, right?
No.
So why this is so? See, if field were not normal to the equipotential surface, says that it would have a non-zero component along the surface. Let us draw some electric fields, constant electric field, right? And I told you
Yeah.
that the potential surface to this is like this. Okay, this is one of the
Yeah.
equipotential surface. So the electric
Yeah.
field is always normal to it, isn't it?
Yeah.
If you take a point A, point B, and a point C, so at any point here, VA is equal to VB is equal to VC. Okay?
Okay.
Because if it's not that the case, then there would be component of electric field along the surface. All right. And
Yeah.
so to move a test charge, a work would have to be done. I mean, this thing would be violated. The first thing, work would have to be done in moving a charge from one point to another. Electric field is not perpendicular to the equipotential surface because, like, there will be some component of electric field in this direction, isn't it?
Yeah.
But it's not so in equipotential surface. Electric field is like this.
Okay.
There is no component along AB, isn't it? No
Yeah.
component of E along the line ABC, let's say, okay? There is no component of this. See, this whole electric field is acting in this direction, right? If electric field were like this, for example, like this, okay, and if this is theta, then this would be E cos theta, and this would be E sin theta. Then there is some component of electric field in this direction, right? In the direction
Yeah.
of equipotential surface. So whenever there is some component of electric field in this direction, if you want to move a charge from A to B, for example, okay,
Yeah.
then since this
Yeah.
electric field is acting in this direction, this would act a force on the charge, isn't it?
Yeah.
In this direction.
Yeah.
And if you want to move it from A to B, you would need to do some work against this force, isn't it?
Yeah.
But that would violate this rule that no work is done in moving a charge from one point to other over
One point to
equipotential
another.
surface. That means that would not be a equipotential surface anymore, right?
Yeah.
This ABC would no longer be an equipotential surface if a work has to be done in moving this Q naught from A to B. And that would be possible only
Yeah.
when there is some component of electric field in this direction or in this direction. Like, there would be 180-degree opposite, but the direction is the same, right? Along this line, the both are along this line. That's why
Yeah.
EF is always normal to this. Okay.
Yeah.
Third one, the equipotential surfaces are closer together in regions of strong fields and farther apart in region of weak fields. This is also important. Potential surfaces are closer in region of strong field and farther and region of weak field. Okay,
Okay. Yeah.
why so? Because see, the relation is E is equal to minus dV by dr. This is the rate of change of voltage, the negative of this. That's called as E. Now, if you want to find dr from here, what would be that? Minus
dV
dV
to
by
E.
E. All right. This is
Yeah. Okay.
this is dr. Now, if we take dV as a constant, okay,
Okay.
that means we are talking of equipotential surfaces. Okay,
Okay.
dV means there is no change in V, isn't it? Because that's the change in
Yeah.
V. When there is no change in V, we are talking of equipotential surfaces. That is the surfaces having the same potential. Let us take
Yeah.
this dV as a constant. Then on this constant potential surface, if we change this dr, the E will change because then dr is proportional to
Yeah. Inversely proportional. Right?
what? Yeah. So that means if R increases, E decreases, and the other way around, if R decreases, E will increase, right?
Yeah.
That means for a change in the distance between 2 points, okay, if you increase the distance,
Yeah.
the electric field would be less, and if you decrease
Okay.
the distance between the 2 points on the equipotential
The electric
surface,
field.
electric field will be high. That's what they
Okay.
say, that equipotential surfaces are closer in region of a strong field. So that means
Okay.
he has not drawn this. I'll show you later what's that. Okay,
Okay.
you can also see the diagram for 0.26. See,
2.26.
so the dashed
Okay.
dashed these circles,
Yeah.
those are equipotential surfaces. Let me see if I can copy this. You can
Yeah.
understand this thing, this example. So these whole lines, these represent electric field. This dashed line, this represent equipotential surface. And you can see there are two charges, one is positive, other is negative. All right, so the electric field is going from positive to negative like this. Okay, and these
Okay.
circles, these represent equipotential surfaces. As you can see, the lines, these lines, these are close apart, right?
Yeah.
And you see these circles, these dashed circles, these dashed circles are close at this point, right?
Or farther away at the other.
And they are farther away at the other.
Yeah.
Okay, so when they are farther, like the distance between the two potential surfaces is large, that means the electric field would be how much, large or small there? See, if R is large,
Small.
E would be small. As you can see, E is very small there, isn't it? The
Wow.
number of lines are small here as compared to in this region, right?
Yeah.
So here lines of electric fields are very close apart, and hence the distance, see, the distance between the two equipotential surfaces is small, and hence the electric field is large. Large means these lines are close apart, isn't it? The electric field lines.
Yeah.
And here, this dr is large, the electric distance between the two surfaces. But the electric field is small, as you can see. These are very far apart, right? These
Yeah.
electric field lines. So that's what it is. That they are equipotential surfaces are closer in strong fields and strong in weak fields. And the last is no equipotential surface no two equipotential surfaces can intersect each other. Right?
Yeah.
Because if they intersect, like here, if you see this example, we can draw many equipotential surfaces like this, right?
Yeah.
Equipotential surface means what? Suppose this is 5 volt, then everywhere this is 5 on this line.
5.
If this is
Yeah.
3, it is everywhere 3. But if they were to intersect, that means that this would make a conflict. It is 5 volt as well as 3 volt at the same time.
Is that
Isn't it?
possible?
No, that's not. That's why they cannot intersect.
Since not. Okay.
If they intersect, then it would mean the same potential, different potential for the same point. Okay,
Yeah.
that is not possible.
Yeah.
A point can only have one potential, one value of potential, either 3
Yeah.
volt or 5 volt. These are some properties of equipotential surface. Now let's see, let's draw. Okay, draw equipotential surfaces for various charges. Okay, let's first start with a point charge. All right,
Yeah.
so let's take a positive point charge. So this is some positive charge. Again, this nomenclature is fixed now. This dashed line represent equipotential surface, and this what you can say, this,
Straight line.
yeah, this represent the electric field. So this is what the electric field looks
Can you give
like.
me a minute? On your back.
Just a second. Yes.
Give me a minute. I'll be right back.
Okay, sure.
Yeah.
Want to draw potential surface to it? What would that be? It would be concentric circles.
Yeah.
Like this. Why each of this circle is equipotential surface? Can you tell me the reason?
Why?
Why each one of this
Yeah.
is an equipotential surface?
Because it says it's an equipotential surface.
No, like, why is it so? Why is it not some straight line even? Why they are only circles? Is the potential at this point same as that of this point?
Yeah.
And what about points C and D, which are on another circle?
Are
Let's
you
say,
drawing something, or are you like asking me from the textbook?
know what I've drawn. Look at that.
Because I think your screen is stuck.
Cannot you see the? You see, I'm bit up and down.
No,
No.
no.
Oh, just. What can you say about C and D? Is the potential VA is equals to VB is equals to VC?
Where is C?
Oh, C is
Oh, is it like reduce A? Yeah. Yeah, it will all be equal, right?
this is C, right? Just this is C, okay,
Yeah,
and this
and
one
that's
on the
D.
same circle, that's D.
Yeah, it will be.
You are absolutely wrong. What have you studied then?
What? No, what do you mean I'm wrong?
This first,
It's an
second,
equipotential surface.
each one of them is an equipotential surface. Okay,
Oh.
so VA
Oh.
is equal to VB.
Oh,
VC is
but
equal
it's
to
not
VD.
equal to VC.
Why that would be? See, what is V for a point
Because it's
charge?
on the. I know, because it's on this different circle. On the
Yeah,
different equipotential circle.
what is
Oh,
now I'm
okay.
asking, why is this circle only? Why is it not some anything else?
I don't know, maybe
1
because it's
by
like
4 pi
really
epsilon naught
awkward.
q by r. This is the formula for potential to a point charge. Do you remember?
Yeah,
Now, since
yeah,
q is this charge, which is a fixed constant value, this is also constant. This is a constant. So v is
yes.
proportional to
But
inversely proportional to 1 by r. V is inversely proportional to r, right? That
yeah,
means as if we fix the distance, there will be same potential difference, isn't it? Like this.
yeah,
Is one circle. Let's not draw the electric field. This is other circle. This is a fixed radius, right?
yeah.
Circle is there. So when this is also fixed, is not the potential going to be the same? V is
For that area.
V is this 1 by 4 pi epsilon naught q by r. This q value is
Yeah,
fixed. This is fixed, right?
yeah,
Now if you take r as some 4 centimeters, it will be the same at every point. This is also 4, this is also 4, this is also 4, also 4. So the same potential value will be the same, the value for V, isn't it?
yeah.
But if you
Yeah.
change r, this is, we change this radius. Now this come to this circle, which is r1. Okay, V will be 1 by 4 pi epsilon naught q by r1. Q 1 by 4 pi epsilon naught is constant, and r1 is same on each point, every point.
Yeah,
So there will be the same
yeah.
potential. That's why this circle is the equipotential surface. Okay,
Okay.
potential will be the
Yeah.
same at any point on the circle. Now let us see what is case for two charges, combination of two. This is a single charge, point charge. Now let us see the equipotential surface for charges. Okay, so for two charges we can have two cases, like the charges can be equal and opposite, which is the case of electric dipole.
Yeah. Uh-huh.
Equal and opposite charges. All right.
Yeah.
Now let us see if I can copy paste it. No. Let me
Okay.
draw this. This is positive charge, this is a negative charge. This constitute dipole, and the electric field is V this. Okay.
Yeah.
It is going from positive to negative, right? Going all
Yeah.
they are not intersecting. It's just my drawing. Okay.
Okay.
Now outside it is going like this. Okay.
Okay.
On this side also. So from the positive charge it will emanate and end at the negative, so it will come into it. This is the electric field. Now you want to draw the equipotential surface to it. Okay. Let me draw
Yeah.
it with a white pen. This is the equipotential surface dipole. This one, and would be like this, and you can draw as many as you can. Third one. So as you can see that they are closer apart inside, right, in the region between the two line joining the two charges. I'm talking about this region. This region,
Yeah.
the equipotential surfaces are close apart, and in this region they are wide apart.
Yeah.
The reason I told you earlier. Okay, this is, you can take this example. Okay,
Yeah.
this is, they both are same. Okay, so like this you can draw circles. All right, these are the
Yeah.
equipotential surfaces. These circles are the equipotential surface. Okay, now
Yeah.
this, what about when the two equal charges are not opposite, they are like, third, fourth, two and like charges. All right,
Yeah.
what would be the case? It somewhat different. So let us first draw that. Let us draw two positive charges because there will be like charges. Electric
Okay.
field would be
So the
would look
one
like
repel
they would exert force on each other.
ish.
That's why they would electric field would not come together. Okay,
Okay.
electric field will tend to go away from each other, right? Like this.
Yeah. Yeah.
Because they will repel, right? So this is the case inside. Outside, like the same thing. They are going away, they are emanating from positive. Alright.
Yeah.
But what can you say about the equipotential surface in this case? Let us draw it with the green pen. They would be like this.
It would be
This is one of the equipotential
like
surface. This is another. Okay. This is the third one. As you can see the difference between the two. See, here inside the equipotential surfaces were closed apart because the electric field was strong inside the region.
yeah.
Here it's the opposite case.
But here it would be farther away.
Yeah, side electric field is lesser, like the magnitude is less, so the equipotential surfaces are far apart. But outside the
Yeah.
electric field is higher, and hence these are close apart. Okay. The same you can draw on this side. I'm not drawing it.
Okay.
You can draw these circles here also. That happens. Far apart side there.
Yeah.
Like, okay.
Yeah.
So we have completed. Now the final thing is the drawing of equipotential surface for uniform electric field, not the charge. Okay, and this is already we know for an uniform electric field. Uniform electric E. So the equipotential
Yeah.
surface is like this. Actually, it's in 3D. Okay, the plane, whole plane inside the screen.
Yeah.
Like this. Okay.
Yeah.
This is the equipotential surface. You can draw many. This is the one, because it would change as soon as you change the distance, isn't it? As you change this distance
Yeah.
from A to B, A is another equipotential surface, B is another equipotential. This is C, this is D. Okay, from the top it looks like this, as like A and B, but from the sides it's the whole plane inside. Okay, because this electric
Yeah.
field is also inside going. This is in 3D. Okay,
Yeah.
this is the equipotential surface.